Hey guys, Mr. Mailhot back here again, pre-calculus. We did an example last time from our shifting with function notation homework. Let's do another example, especially since we learned a little bit more about domain and range. So let me forward this. Let's do the last example. Okay, here, h of x is 2 times the absolute value of x. Remember, absolute value of x, shape of a v. I don't see anything inside there or outside here, so it hasn't been shifted left or right. It has not been shifted up or down. It's just been stretched, made to be a little skinnier. So the starting point is still at the origin. Remember, this 2 tells you the slope is going to be over 1 and up 1, 2 to get to your next point of your graph, over 1 and up 2. It's symmetrical, so we can do it. The difference between, and this is a common thing I've been seeing, the difference between the absolute value and quadratic continues to widen. It's not a constant slope out here. It slowly gets wider. Absolute value is a constant linear slope. So when we go over 1 up 2, you could keep doing that and get a real nice graph. Now you could also get a ruler out or just use your best estimation, but because it's linear, because they are straight lines, you can use that slope repetitively, unlike with quadratics. Okay, domain and range. Remember, domain is through the x-axis, the x values, range is your y values. So let's go through our x-axis. If I'm going along this x-axis like this, x equals 3, x equals 6, x equals 9, I could go up here high enough and eventually hit my graph. Like, it would be up there. Same with negative. And I think you could go all the way out here to infinity, and you'd have to go pretty dang high, but you'd get there. Domain goes from negative infinity, right? You could go way back here and look up and still hit your graph high enough eventually. Negative infinity to positive infinity. Let's do y values. Okay, like y equals 2 and 4 and 6 and 8 and 10. That's looking all good up all those positive values. I'm hitting my graph as I go that way. The first part where I don't hit my graph is right when I pass this x-axis. Well, the y value of x-axis, this is actually the line y equals 0, right? It goes right through 0 on the y-axis. Anything below here, it doesn't hit the graph. The graph doesn't even go down here. So the smallest value that is in the range, 0. The largest value, infinity. Now remember, when we have a defined value for a domain and range, we use a bracket instead of a parentheses, because I could actually draw a line through 0. Let's go next. Okay, we are shifting this graph a little bit. We're going to move it to the right 5 and up 2, but it still has the same slope. It still has that variable of 2. So we're moving the starting point over 1, 2, 3, 4, 5 and up 1, 2. There's our new starting point, over 5 up 2 from our shifting directions. The slope is still over 1 up 2, over 1 up 2. That'll be good enough for our purposes. And there we go. All right, graph is done. Let's do domain and range. Remember, domain x, range y. Here we go, x values. Okay, my graph's not over here, but that's because my paper's not physically big enough. You could extend this line way up there and go here through x equals negative 6, and it would eventually hit it. Same with infinity, it would hit it. Negative infinity, and you guessed it, positive infinity. I think some of you are going to notice a pattern with absolute value graphs and quadratic graphs, that this is a common theme. Range. Well, let's see. What is the smallest y value that I can go through and still hit my graph. I'm down here. There's nothing down here, so I'm out of luck. I'm thinking the smallest y value is not 1. Look, my graph didn't go through there, and nothing's there. But 2, it did hit it. So 2 is the smallest value. Remember, hard bracket, 2. And now how high up can I go and still hit there on the y-axis? I could go all the way up to infinity. You could go way up here. Your graph extends. It's good enough. Okay, last one. Now remember, we're shifting this function in this way. We're not shifting this shifted function. We're going back to our original h of x. Here it is, h of x. And we're shifting that one. So this does a couple things. Number one, the negative sign is going to flip it upside down. And the 4 is going to move it down 4. Let's do it. The original starting point was 0, 0, so there we are. This says move it down 4, so we're down here to 4. And it's going to be going facing downwards. That negative leading coefficient made it go down. Still 2, but just negative 2. So over 1, down 2, and over 1, down 2. Something like this. Flipped it, brought it down 4. Let's do domain and range. Domain, think about it. You got it. It's the same for all of them. I could go way out here to negative infinity and go low enough off the desk, and I would still hit my graph. Same with positive infinity. So domain, negative to positive infinity. Those soft parentheses, soft brackets. Range. This is where it was weird. You might get a little thrown off because the graph got flipped. Think about it still. Domain is your y values. If I'm up here at 6, y equals 6, not hitting my graph. Y equals 4, nah. Y equals 1, nah. Y equals 0, no. Negative 2, oh my gosh, I'm still not there. How far down do you need to go? Negative 4. That's the smallest. Well, is it the smallest? I guess it's the first one we hit. But you can go lower, right? Since the graph opens downwards, you can go lower. Down to negative 10 and 11 and 12 and infinity down here. Your graph would still hit it because it continues off in that direction. So really the smallest value in your range will be that negative infinity. And the largest value, the one that's highest up on the y-axis, is negative 4. Hard bracket. I know that's a little weird because you'd think a negative, well, that's the smallest one. Not really. Compared to negative infinity, negative 4 is larger. I'd rather be in debt $4 than infinity dollars. All right, guys. Come to class with more questions. We'll go through some more together. I appreciate you. Remember, we're mathematicians. We can do anything we want. See you later.